Lecture 8 is going to focus on the physical properties of coordination compounds. During Lecture 7 we took some time and developed the idea known as crystal field theory. And crystal field theory is going to help us explain the physical properties that are observed in coordination compounds. The two specific physical properties that we will look at are the magnetism of coordination compounds and their visible spectroscopy. Make sure that you read Chapter 4. I'm also going to give you homework set number 4 this weekend. Make sure you work on it. This will probably be where Exam 1 material ends. So magnetism in compounds. Much like in atoms or ions, where the magnetism is determined by the number of unpaired electrons, magnetism in compounds are also determined by the number of unpaired electrons that it has. We're actually going to put numbers to the magnetism for these compounds. The idea that we'll be working with is molar susceptibility, and that's a measure of how much 1 mole of a substance interacts with a magnetic field. We measure the molar susceptibility of a sample using a Gouy balance. So here's how a Gouy balance works. You take and you put your sample in a can and suspend it from one end of the balance. On the other end is a weight equal to the mass of the sample. A magnet is placed around the end or around the sample. What can happen is one of two things. If the substance is, or if the container with the sample moves up and this end appears heavier with the weight on it, that means that the substance is slightly repelled by the magnetic field, and it should be diamagnetic. The other case that can happen with a Gouy balance is that the substance can be attracted to the magnetic field, so it would be pulled down more by turning on the magnet, making the sample side appear heavier than what it is. When the sample goes down and is appears heavier than the weighted side, that means the sample is paramagnetic. Now, we talked about measuring susceptibility, and the Gouy balance measures gram susceptibility. And you can take and use the molar mass of a substance to convert gram susceptibility to molar susceptibility. The molar susceptibility is also related to another property of a compound, which is its magnetic moment. The magnetic moment is a lot like a dipole moment. Remember, dipole moments are where electrons are shifted towards one atom or shifted in a molecule in one way to create a dipole. A magnetic moment is the magnetic response to a compound due to the presence of unpaired electrons. There's a mathematical formula that you can use to calculate the magnetic moment of a compound. The magnetic moment, mu, is equal to 2.84 times the molar susceptibility times the temperature, and everything in parentheses is raised to the 1/2 power. The units on magnetic moment are Bohr magnetons. It's just a measure of how a substance responds to a magnet. The molar susceptibility is in units of Bohr magnetons squared per Kelvin. And the temperature must be in Kelvin. When looking at magnetic moments, remember that Bohr magnetons, Bm, are the units for magnetic moment. There's two components to magnetic moment in ions with unpaired electrons. You have a spin-only magnetic moment, where the magnetism is derived from the spin of the unpaired electrons themselves. And the other is called the orbital magnetic moment. And that is the magnetic moment arising from the electrons orbiting the nucleus. Spin magnetic moment is a large contributor to the overall magnetic moment of a compound, whereas the orbital magnetic moment is a very small contributor. So to calculate the overall magnetic moment for a compound, both the spin and orbital components must be accounted for. Mathematically, this is how it's done. The magnetic moment, taking into account both the spin and orbital components, is equal to G, which is called the gyromagnetic ratio, times the square root of the total spin quantum number, so you add up all the spin quantum numbers for the unpaired electrons, times the total spin quantum number plus 1, plus 1/4 times the total angular momentum quantum number times the total angular momentum quantum number plus 1. This is a complicated formula, and I know you could use it if I gave you what the gyromagnetic ratio is, because it's actually very close to a set value. However, since the orbital component to the magnetic moment is very small, many times we just ignore it to estimate the magnetic moment for a compound. So, like I said on the last slide, we can focus on the spin-only magnetic moment because it is the major contributor to the overall magnetic moment. UL, very small. The spin-only magnetic moment, μs, is calculated very easily. You take the square root of the total number of unpaired electrons times the total number of unpaired electrons plus 2. Very, very simple. So all you have to do is count the number of unpaired electrons a compound has, add 2 to that, multiplied by the total number of unpaired electrons, and take the square root of that.